All right. So I've been asked today to talk a little bit about some of the new developments that have been coming along in terms of using mineral chemistry to aid in exploration. And I'll apologise now for those of you who are passionate about hearing about Queensland exploration. I'm not going to be talking about Queensland today, and I'm going to be talking about porphyry deposits as my example of where the mineral chemistry work has been going on, because this has been a campaign that we've been doing at Codes now for about a decade and a half, so I have quite a large data set to talk to you about. Sean Barker will be giving a presentation in a few weeks about some of the work we're doing up in the Northwest Queensland Mineral Province in collaboration with GSQ and UQ on footprints of Queensland ore deposits. But what I'm hoping to go through in the next little while is to just give you an understanding of why mineral chemistry has been evolving as another tool that we can add to the exploration toolbox. Joe's gone through very comprehensive appraisal of all the different approaches that we can use in terms of aiding geochemical exploration. So I've got a few more to add to that toolbox. And I have to say, really, some of these tools can help you in sorting out what type of mineralisation might be present in the district. Others may actually be able to help you work out if there's a substantial resource and which direction to go looking for it. Now, we are working all around the world with a variety of mining companies. So we're working in places like Chile, and here's a Google Earth image of the Atacama Desert in northern Chile. So what we have is the high Andes Mountains. They get up to 5,000 or 6,000 metres in a very arid desert, and those mountains are eroding. So what you're looking at here is the flanks of the Andes Mountains, and we've got these huge sheets of tertiary gravels and ignimbrites. So the cover they're dealing with in northern Chile can be this type of recent tertiary to quaternary gravels and recent volcanics. And those gravels can be up to 600 metres thick. So it's a different type of challenge for exploration undercover than what we might be dealing with in the Australian context. And back in the old days, we could have taken the joy of wandering up that canyon that's carved through those gravels and recognised this red limonite stained area, which is actually the leached cap on the top of a Paleocene porphyry copper molybdenum deposit called Mocha. So any good field geologist who's been trained in what an outcropping gossan looks like would pick that as the weathered products of a sulfide-rich ore body and would have made the discovery of the Mocha porphyry. But there we're looking at an erosional window through tertiary rocks to see that Paleocene basement and to see the top of that weathered ore zone. There's an awful lot of effort now taking place to try to see through all of that gravel cover that you can see across every ridgeline there and to try to work out whether there are some behemoths lurking underneath. In the Australian context, well, we can take a look at the Cadia district in New South Wales. Newcrest made a series of spectacular discoveries of 4 porphyry copper gold deposits there in the early to mid 1990s. We're looking here at the top of the Cadia Hill open pit. So Cadia Hill is the first of those porphyry deposits to be mined. And the Cadia deposits are latest ore division to early Silurian in age, but they were buried in the middle Silurian beneath a Silurian marine basin. So those red and white rocks on top here are actually cover. And the Cadia deposits are partly obscured by Silurian and tertiary cover. They're partly outcropping and they're a little enigmatic. The sad thing about the Cadia district is gold and copper were first discovered there in 1851. So there was 140 years of exploration before Newcrest came along and put all the pieces of the puzzle together, and in the space of 4 years made 4 spectacular discoveries, including the Cadia East copper gold deposit, one of the biggest gold-rich porphyries on the planet. So we really need to do better as we are exploring undercover. We need to understand our mineral systems, and we need to try to maximise the opportunity of the weak distal signatures of these rocks that are preserved as alteration halos to help us vector towards the mineralised centres. So because I'm going to be talking about porphyry deposits, I just want to give you a few key elements of porphyry systems to keep in mind. These are ore deposits associated with hydrous oxidized magmas that are emplaced in magmatic arcs and post-collisional belts. They're emplaced at depths of maybe 3 to 6 kilometres below the surface. The magma compositions are quite distinctive in that they need to be very wet magmas to produce large amounts of hydrothermal fluids, and they need to be highly oxidized to transport copper, gold, molybdenum, and sulfur together incompatibly in the melt. So the magmatic chemistry of these rocks is distinctive, and we can use whole rock and mineral chemistry to help fingerprint what a fertile magma looks like in a porphyry system. We get peripheral styles of mineralisation around porphyry deposits. We get epithermal deposits of high, intermediate and low sulfidation character. We get skarn, we get carbonate replacement deposits. But those zones of mineralisation are small bodies of well-endowed rock that float within a sea of alteration. We have a huge three-dimensional domain of hydrothermal alteration that has affected the rocks around the porphyry and peripheral deposits. And again, we produce distinctive mineral chemistry of those altered rocks, and we produce geochemical signatures in the whole rock samples as well. And if we can use those geochemical data and the understanding of mineralized systems, we can potentially navigate our way into the ore zone. So there are opportunities using mineral chemistry to aid us in this exploration. And over the past decade or so, there's been quite a lot of effort going on in Australia, in Canada, and in other parts of the world, trying to help develop mineral chemistry as a tool to aid porphyry exploration. There's a large group of researchers actually trying to look at indicator mineral chemistry, taking the approach that has been used very successfully in kimberlite exploration, looking for diamonds, and trying to develop indicator minerals that are indicative of porphyry systems. Okay, so helping us to identify the presence of or potential for porphyry deposits. Now, I refer to this as fingerprints, if you like. It's the DNA of a porphyry deposit. What is the geochemical signature recorded in the mineral that tells you this comes from a porphyry system? A lot of effort going on in this space in Canada because they're looking at indicator minerals, particularly from the perspective of till geochemistry, trying to help use glacial till to detect whether you've got erosion of a porphyry deposit upstream in the till. The work we've been doing down at Codes has been looking at a different approach. We're trying to use in situ alteration mineral chemistry. So we're actually not trying to sample transported media. We want to take samples in situ and look at the distal alteration signature of porphyry deposits to see if we can extend the geochemical footprint of systems in a district so that we can actually come up with vectoring tools, trying to predict the likely location of the ore deposit. And we're also quite pleased to see that the mineral chemistry maybe is also giving us signs of fertility. Okay, so how well endowed is the largest system in the district? Okay, so the vectoring side of things is really looking at the geochemical footprint. How big is this system? So we're calling those porphyry vectoring and fertility tools. So the acronym is horrible. It's, I think, is the pronunciation. Now, all of this research has been going on over the last couple of decades. It's not a new idea. People have tried to use mineral chemistry before. There was a lot of work going on in the 80s and 90s. But what's come along is enabling technologies in terms of the ability to do low detection limit analyses of a whole swag of elements in individual mineral grains using laser ablation ICP-MS. So the advent of that technology in the late 90s was revolutionary. It's given us detection limits well below parts per million for individual trace elements. And we've been developing new data reduction and quality control techniques that are really starting to facilitate rapid data processing, because data processing of laser ablation data is quite challenging, so that we're able to really start to generate quite substantial data sets. In the porphyry world, the other key enabling technology is all of the shortwave infrared developments that have been going on that really aid us with clay mineral identification. And that's been a boon for helping to map the clay alteration halos above and around porphyry deposits as well. I won't be going into talking about those today because I just don't think we're going to have enough time. So just a little bit on the indicator mineral chemistry approach. This cartoon sort of tries to illustrate the concept that you might take, finding some sort of a distinctive mineral that can be weathered out of a porphyry system, and maybe it's transported and is preserved in stream sediments or in soil or in till. So for this to work, your indicator mineral has to have a distinctive trace element composition that discriminates it from country rocks. In porphyry systems, we need to discriminate it from other intrusive complexes that don't produce mineralization. If it's an alteration mineral, we need to discriminate it from different types of hydrothermal systems. And if it's going to be transported, if it's in transported media, it's got to be resistate. So the perfect indicator mineral for a porphyry system is actually zircon, the most robust mineral out there in terms of resisting weathering. And I'll go through a little bit on zircon chemistry as to why it is quite helpful in porphyry exploration. But there are other minerals as well: magnetite, apatite, tourmaline, garnet, epidote. These all show potential as indicator minerals. There has been a bit of work on things like plagioclase and chlorite. They do have potential, but not in transported media. They don't survive in the weathering environment. The reason zircon is such a useful tool and is really being taken up quite widely by the major companies exploring for porphyry deposits around the planet is manifold. Zircon is the best high temperature geochronometer available for magmatic rocks, and it turns out that porphyry deposits generally form in metallogenic belts at around the same time. So understanding the age of your magmatic rocks is really important because you've got this period of opportunity when ores form. So just knowing you're in the right age window is very helpful in porphyry exploration. We can do isotopic analyses of zircon, we can do trace element analyses of the zircon that really help us understand the magma petrogenesis. And one of the key things that can come out of trace element chemistry on zircon is whether the zircon comes from an oxidized or a reduced magma. And porphyry deposits are associated with some of the most oxidized magmas on the planet. That allows the metals and the sulfur to be transported together in the melt from the zone of partial melting to the upper crust. So it's an essential prerequisite for forming a giant porphyry copper, gold, and molybdenum deposit. We can get temperature out of zircon, we can get understanding of the magma composition. Where I guess people really get excited is trying to put some of these parameters together to work out whether you've got a prospective magma in terms of its potential to produce mineralization, a fertile magma, demonstrated capacity that it has produced mineralization, or a barren or unprospective magma. The diagram on the left you can see was published by Liu et al. In 2016, where they were looking at parameters in zircon chemistry that reflect the water content on the y-axis, the oxidation state of the magma and the degree of fractionation on the x-axis, and coming up with a field up in the top right corner that says these are the type of zircons that come from a fertile magma. Now that all looks pretty good, but those diagrams tend to be a little terrain specific, so you can't just take all of your data from a given province and plot it on that diagram and expect them all to work the same way. But there's a lot of excitement and interest in this type of approach, especially in terms of greenfields targeting, trying to identify new areas previously unrecognised that have had magmatic activity and have the right geochemistry to potentially produce porphyry mineralisation. The diagram on the right, Ping Shen was looking at the Central Asian orogenic belt porphyry deposits, and she made the observation that the more oxidised magmas, as reflected in the cerium 4:3 ratio in the zircons, generally come with the giant porphyry copper deposits, and the smaller deposits tend to have more reduced composition. So there's some interest there in terms of, you know, maybe we can discriminate large and small systems based on zircon chemistry. But as we get into this research, you always get caveats and exceptions. Matt Loader published a paper just a couple of years ago highlighting that co-precipitation of various phases can strongly influence the trace element chemistry of the crystallizing phases. And when zircon is crystallizing coincident with titanite, then the titanite preferentially scavenges some of the rare earths, and so you wind up with variations in the zircon, europium and cerium anomalies. So that means there's potential false positives that can be generated from this type of mineral chemistry. And because it's fairly early days in this mineral chemistry space, we've probably got a whole lot of false positives and hopefully not too many false negatives, but they may be out there as well, that we've got to work our way through and come to recognise. So the research is continuing, but zircon is an area of considerable interest across the globe now in terms of this type of exploration. Other minerals that have been looked at as indicator minerals, well, plagioclase. Ben Williamson did a nice little study published in Nature a few years ago that was highlighting some unusual variations in plagioclase chemistry if you were looking at plagioclase associated with porphyry deposits versus plagioclase from just normal arc magmas. And he was highlighting that there can be excess aluminium in plagioclase when you get really high water contents in the melt, and that can cause copper to be excluded from the plagioclase crystal structure, actually enhancing the capacity of a magma to exsolve copper and potentially produce an abundant copper-rich fluid. Really intriguing idea, but the problem with plagioclase is, of course, it's not preserved in most hydrothermal systems around porphyry environments. It gets altered. It's one of the more alterable minerals. And this type of approach really requires a pristine plagioclase to be able to analyse it and see if it's got excess aluminium. So really intriguing in terms of helping us understand magma petrogenesis and potential impacts on metal fractionation out of magmas. But I don't think that plagioclase is going to be something we're going to be using in routine exploration anytime soon. Magnetite's another potential indicator mineral. It occurs both as a magmatic mineral and as a hydrothermal mineral. And some of the earliest work on indicator minerals in porphyry deposits goes back to the work that CSIRO was doing in the RIMS project back in the late 1990s. The little cartoon in the top right was out of Andrew Cross's master's thesis at the University of Canberra. It was part of that RIMS project, just showing the aluminium, titanium and vanadium titanium ratios of magnetite and showing you could really discriminate quite easily the magmatic magnetite, which tends to be more titanium rich, from the hydrothermal magnetite in porphyry and skarn systems, which tends to be much more enriched in aluminium and vanadium and lower in titanium. The diagram on the bottom right, that's from Sarah Dare's work, where she was looking at a variety of ore deposit types and showing again this distinction of magmatic magnetite and hydrothermal magnetite mineral chemistry. And there's been quite a lot of publications in the last decade where people have shown this fingerprinting capacity of magnetite, that potentially you can get different ore deposit types and different magma types fingerprinted by analysing your magnetite. And it's resistate, it's magnetic, so it's easily separated, so it's an attractive candidate for PIMS. But the SEM image I'm showing you in the top photo, well, that's a bit of magnetite from magmatic magnetite from the Grasberg porphyry copper gold deposit in Indonesia. And it highlights why, for mineral chemistry work, it's a bit of a problem for laser ablation analyses. When we do laser ablation analyses, the spot size might be 30 or 50 microns. These days, sometimes at codes, we get it down to 4 microns, but you can see a large spot size has got a problem with magnetite, especially magmatic magnetite, because it's got ilmenite exsolution lamellae. So when you bore a hole into that with a laser beam, you're getting more than one mineral. And so that can mess up your analyses. It also turns out magnetite doesn't hold its chemical composition very well. It seems to be quite prone to diffusion or resetting of its trace element compositions by post-crystallization hydrothermal fluid. So That can be a positive and a negative. We've looked at magmatic magnetites 10 kilometres away from the porphyry deposit and found a hydrothermal signature in a mineral that looks perfectly unaltered. So there can be a positive in that, but there can be a lot of a negative as well, because you may not preserve the signature you want. Apatite is another potential indicator mineral. There's a little study that Farhad Bazari from MDRU published in 2016, and you're looking at some of his images and a graph from that work that was in economic geology, just highlighting again that you can discriminate magmatic and hydrothermal apatites, and that the different flavours of apatite we get in porphyry systems, whether they're associated with potassic alteration or phthalic alteration, can actually pull apart in geochemical space and bivariate space, but it turns out you can do it in multivariate space as well. And that's what Mao et al. 2016 was doing with his discriminant projection analysis study of apatite. Another thing about apatite is you can see the luminescence properties in these weird yellow images. So apatite you can get cathodoluminescence behaviour, and magmatic and hydrothermal apatites luminesce in different fashion. So you can get quite a detailed record of the paragenetic history. Maybe there's been a lot of recrystallization, dissolution and reprecipitation. And you can see that you really need that cathodoluminescence imagery if you're going to go analysing these apatites, because there's an awful lot going on in those individual grains. So these are some of the minerals that people are chasing in terms of looking at that indicator mineral approach. They're really trying to come up with the geochemical signature of a porphyry deposit recorded in these minerals, and there certainly does seem to be promise in that approach, and for a variety of hydrothermal ore deposit types, with different ore deposit types having their own particular suite of minerals that are going to record that DNA of the ore deposit, if you like, that distinctive trace element signature in something that might survive the weathering environment. But now I want to move on to talking about the vectoring and fertility tools. And so the research we've been doing down at Codes has been really trying to address a couple of key questions that industry continually faces, and they were really nicely articulated by Steve McIntosh from Rio Tinto a few years ago, where he was saying we really need better geochemical vectoring tools to maximise the knowledge gained from deep drilling, and fertility. Can we fingerprint well-endowed systems? Well, the cross-section you're looking at is from the Pebble porphyry copper gold deposits in Alaska. The Pebble West deposit is outcropping, and it was discovered in the 1980s in a pretty remote part of Alaska. The grades are okay. The resource is, marginal. You couldn't actually bring this online as an ore deposit, and it had quite a, several decades of exploration, people poking around trying to work out if they could make Pebble West fly. In 2005, 2006, Pebble East was discovered. And you can see that Pebble East is a really high-grade monster porphyry copper gold deposit. Really sweet grades, biggest, if it's up there with Grasberg as the biggest gold-rich porphyry on the planet, but a significant challenge of cover. You can see up to 600 metres of post-mineralisation cover in those green rocks. So the key thing you want in exploring in a place like Pebble West is tools that can help you know, actually, we're missing the elephant in the room. The elephant's hiding, it's got a blanket over its head, and we're stuffing around here with the mouse, and we need to move on and start looking in the right place for the thing that's going to potentially be a significant mine for many years. So we're trying to do that through mineral chemistry. And so we're looking undercover, but ideally, the things we're doing are looking on below cover where there's a little bit of outcrop distally, or where there's drilling through cover into the bedrock. And the reason we're doing that is because without the complications of weathering and geochemical dispersion, the altered rocks around a porphyry system record subtle, low-level hypogene geochemical dispersion signatures. And they're preserved in a variety of minerals, and the little array of mineral photos you can see here are a bunch of the minerals we've been working on for the past decade or more. We found that analysing these alteration minerals potentially gives you information that can be used for both fertility and for vectoring. The key thing comes back to how do you sample? You need to sample to background. You need to be able to recognize your geochemical background. And that proved to be a really challenging thing initially when we started this work. If you tend to make presumptions about where geochemical background will be, and these data take a while to generate. So there was a lot of learnings in sample distribution that came along for us in terms of this work for porphyry systems. What it means is we now have an additional set of tools that can be added to the Porphyry Explorer's toolbox, and they really should be used early on to try to help assess whether we're in the right sort of postcode, whether there's something substantial there. And while the individual analyses can be expensive, it turns out you can achieve this goal of helping to work out if there's something substantial with a low density sampling program, and therefore relatively low cost relative to many other of the available geochemical search technology. Our research has been very generously supported by the minerals industry through Amira International, now Amira Global. We're currently in the 5th iteration of our Amira program, P1202, and our research has been really driven by those questions of fertility and vectoring. Can we detect large systems? So how big is it going to be? How far away is it going to be? And in which direction should we go? And we've worked in the porphyry environment, both in what we call the green rock and the lithocap environment. And I'm going to talk about the green rocks because we've not got time in the remainder of this talk to cover both environments. Green rock environment is essentially the propylitic halo that occurs around the core of a porphyry system. And so it's green because the andesitic or volcanic rocks that typically host porphyries in island arcs, the minerals within them, the hornblende and the plagioclase, they get altered to epidote and chlorite. And so we're producing green coloured alteration minerals that give the rock a greenish tinge. You're looking at some lovely fault fibres on epidote here with a nice background of fine ground mass alteration to chlorite, the dark green colour. So that type of rock is really common peripheral to porphyry systems. We look at it and we go, well, what relevance does that have? And here's an image of the island of Sumbawa in Indonesia. So we're looking at the southwest corner of Sumbawa. So we're pretty much on the equator in the tropics, and we're looking at the Batu Hijau open pit. Batu Hijau is a beautiful, well-behaved copper-gold porphyry deposit. It's a giant resource, about 1.6 billion tonnes at about 0.4 copper and 0.3 gold. And it is a deeply eroded porphyry, so we've lost the top off the system, and we have a potassic core surrounded by a propylitic halo. The host rocks are really homogeneous basaltic andesitic sort of volcaniclastics surrounding a tonalite complex. Batu Hijau would be an explorer's dream because when we use geophysics, it has a bullseye signature. That magnetic high that you can see in the magnetic image I've just animated in is due to the presence of abundant magnetite associated with biotite in the potassic core. So this has a strong biotite magnetite alteration domain associated with the copper-gold mineralisation. There is a second magnetic high because there's a magnetite-bearing skarn on the southwest side of the ore zone. But in porphyry systems, if you're really lucky, if you're at the right erosion depth and the system produced a lot of magnetite and we haven't got a lot of overprinting alteration that destroyed the magnetite, error mag can give you a bullseye target. So there is the target that you're looking for. Porphyry deposits tend to have a pyrite halo. So we have a core of bornite and chalcopyrite that might be surrounded by a halo of pyrite, and that halo can extend for 1 to 2 kilometres away from the deposit centre. So what it can produce is a chargeability high, and you can see the donut of high chargeability surrounding Batu Hijau. So here you can see how effective both magnetics and geophysics and IP are being in helping to detect the footprint of this deposit, giving us a good 2 kilometre sort of detection limit. Now, it turns out when we use whole rock geochemistry in porphyry systems, the pyrite halo is really responsive to whole rock geochemistry. So this is when we've got sulfides precipitating as a halo around the intrusive complex, we get a whole lot of pathfinder elements, things like arsenic and antimony, defining a geochemical halo that we can detect through conventional rock chip analyses in this case. And there's also going to be a distal manganese halo, so manganese, zinc, lead, arsenic, antimony. These are all things that are anomalous distal, and as you get close to the system, you start to see enrichment in copper and gold and molybdenum. You get anomalous tin and iron and rhenium, a whole bunch of different proximal pathfinder elements. And that rock geochemistry gives us a similar footprint to the IP, about 1 or 2 kilometres out. It should be easily detectable. The mineral chemistry work we're doing at places like Batu Hijau is taking that rock and deconstructing it and trying to look at what's preserved in alteration minerals. So we're trying to get beyond where there's strong alteration and the rock is pervasively transformed and there's a strong geochemical record in the whole of the rock, to where we can only analyse a little bit of the rock. Most of the rock is unaltered, and so we've got a lot of dilution by fresh rock. And what we found in a place like Batu Hijau is we can detect the presence of the porphyry system up to 5K from the deposit centre. So we've basically doubled that search radius beyond which we can generally detect the rock with our routine whole rock geochemistry. Just jumping over to a place called Baguio in the Philippines briefly. This is an example where we've got 3 porphyry deposits, or 2 porphyries in the skarn side by side. So the little map in the top left, the porphyry ore zone is associated with the brown. That's the potassic alteration core, and the yellow is the pyrite halo. So we've got the Black Mountain porphyry, and we've got the Nugget Hill porphyry prospect over here, and then we've got the Mexico skarn over here. And it turns out Black Mountain is a small, moderate grade porphyry deposit, about 30 million tonnes at about 0.4. Nugget Hill looks like a large and high grade porphyry copper gold deposit. Hasn't been drilled yet because the drilling needs to occur on the Philippine Military Academy and the generals are difficult to negotiate with. And the Mexico prospect is an outcropping skarn that turns out to have very weak mineralisation. What we've done here is I'm just showing you a sample transect along A to B and B to C. So we're looking at samples collected from Mexico to Black Mountain and from Black Mountain to Nugget Hill. And the red dots are the whole rock geochemical analyses of these samples. So the red dots are showing you very low arsenic apart from as we come into the deposit centre. And you can see we're getting a lot of arsenic anomalism on the side of Nugget Hill. Sorry, I'm having a little trouble with my pointer here. So you can see how that arsenic is really anomalous as we come into the pyrite halo, and it's really flat outside of Nugget Hill. The triangles, the squares, they are individual spot analyses of epidote, one of the green rock alteration minerals we like to analyse. And you can see that the fertile system at Nugget Hill has a really strong epidote trace element anomaly. We're getting up to 200 parts per million arsenic in epidote in rocks that contain less than 5 parts per million arsenic. So we're detecting that arsenic geochemical anomaly much further out from Nugget Hill than we were with our rock chip sampling. And what's really nice about this is we're actually sorting out the fertility question. Our attention should be focused on Nugget Hill. It's producing the really strong geochemical anomalism. Black Mountain and Mexico are of subordinate interest. So that's one of the things we can do with our mineral chemistry work. Now, the real value in this mineral chemistry work comes from looking at these distal alteration minerals. Okay, so here's a little cartoon just showing you the porphyry mineral system going from this central domain where we get our biotite, magnetite and our mineralisation around the intrusive complex. Those rocks in there, quite strongly altered, should be really easy to pick. We go through a geochemical domain whereby pyrite is present, so that greyish shading is the pyrite halo around this deposit. And so we're going to see limonites if we see this stuff cropping out. And this is a domain where we get a mixture of pyrite with green rock. So we've got chlorite epidote alteration here together with pyrite. But we move a bit further out and we get a loss of pyrite. Pyrite does not extend too far beyond the porphyry system. It stops 1 or 2 kilometres out, and we move into an environment where the rocks have epidote and chlorite alteration, but they don't have sulfides. And the really distal rocks, you look at them and you go, is that anything? Is that seafloor diagenesis? Is that metamorphism? Is that hydrothermal? So that's where we really want to add value with the mineral chemistry work, trying to understand whether there's any significance in this type of rock. All your routine tools, your geophysics, your whole rock geochemistry, they all work really well within a kilometre or 2 of the porphyry environment. Mineral chemistry gives you that chance to do more further out, but it does also add value as we get in close. So if we go back to Batu Hijau, we just take a look at Batu Hijau, if my slides will advance. This little cartoon, I'll just back that up because it jumped forward a little. Sorry. Yeah, this is a slow animation, this one, so sorry about that. Hopefully it's coming. Yeah, so the Batu Hijau open pit is outlined here in the red circle. And what we can see is a sampling transect, or a series of sampling transects where we've done mineral chemistry analyses going out to 5 kilometres from Batu Hijau, and also looking at some other prospects in the district. The biotite magnetite alteration is this brownish domain in the middle. That's the centre of Batu Hijau. And then the propylitic halo, we can map it in a domain of higher temperature actinolite bearing alteration, going out to epidote veins, to epidote replacements, to distal rocks that contain chlorite with very little or no epidote. And when we look at the chlorite chemistry here, and again, I'm sorry if this animation goes wonky, I pressed one too far back. Just got to wait for this one to come back. The chlorite chemistry has really strong geochemical variations as we move out from the centre of Batu Hijau. So those brown circles, you can see the chlorite has 4 or 5 orders of magnitude variation in the titanium to strontium ratio of the chlorides. Now, titanium is going into chlorite at high temperature and strontium at low temperature. So titanium in chloride is effectively a geothermometer. And what we're looking at there is, you know, a 5 order of magnitude change in the chlorite chemistry that we can detect using laser ablation on chlorite. And if we look at the whole rock data, really homogeneous host rock, so there's no protolith effect on this. The titanium-strontium ratio of the chlorite data doesn't change. So all of that change within 2 kilometres gives us, you know, a really strong indication of getting close to this porphyry system. This is effectively a temperature sensor coming into the porphyry deposit that we can't get out of the whole rock data. We can only get it from the mineral chemistry. As we move about beyond 2 kilometres, you can see that the titanium-strontium ratio flattens off and we're essentially moving into a rock-buffered environment. But in close, we're in this fluid-buffered environment. And the data are so good, actually, we can come up with a correlation coefficient for that data set that is, it has an R-squared value of about 0.96. And we can actually calculate the distance to the deposit centre from our drilling or from our rock chip sampling, getting the titanium-strontium ratio of chlorite and plugging it into this equation that we call a proximeter equation. And that gives us predictions of the deposit centre that get as good as within about, you know, 100 metres in the Batu Hijau system. So that's a mineral chemistry tool for vectoring, if you like. When you analyse chlorite and you're getting close to the deposit, it becomes very temperature sensitive and it can give you strong vectoring indications. So if you put these together, if we take a look now, jumping over into the Tian Shan and look at the Taldy Bulak porphyry deposit in Kyrgyzstan, what we did in the Amara projects was we had the idea of giving the sponsors the opportunity to give us blind tests, whereby they sent us samples that were spatially constrained, but we didn't know where the samples come from. And we would do the mineral chemistry analyses and see if we could predict where the deposit centre is located. So Taldy Bulak is an ore division porphyry in the Tian Shan. It's in a region with very substantial orogenic gold and porphyry copper gold deposits. It's not the biggest in the region. Here's some data back from 2008, just showing you the resource. And just showing you the geologic elements in this belt. So Taldy Bulak is in the green rocks. These are Ordovician rocks. There is a metamorphosed Devonian cover that's thrust over Taldy Bulak, and that's this brown coloured material. On the right, you can see the topography with the geology draped on it. The Devonian cover is the brown, and then the Ordovician rocks, the intrusive complex and the volcanics, are in the pinks and greens. These weird little yellow pylons are actually the sample locations. So Andy Wurst, when he was working with Goldfields, sent us a suite of 27 samples with this type of sample distribution. So we sort of asked, try to give us samples with a spacing of about every 300 metres. He gave us 27 samples with that rough sort of sample distribution from surface sampling, and he gave us a sample from the Devonian cover. And he didn't tell us that was from the Devonian cover, but it did have epidote. We analysed the mineral chemistry. We can tell metamorphic epidote from porphyry epidote, so we could screen that out really quickly. High lead, low arsenic, low antimony, doesn't smell like porphyry, so that was excluded from our analysis. The rocks that were sent, you can see on the right here, some of the samples. Sometimes we get really strong epidote and chlorite, sometimes it's really sparse, and we can work with either of those rocks. And just to quickly show you what happens when you put epidote and chlorite together, this is the sample distribution in these little coloured grids. I've highlighted in the black line the outline of the 200 or the 600 ppm copper in soil anomaly around the Taldy Bulak porphyry. This is the soil geochem shown in this map, and just putting it onto our broader grid, you can see that as you get close to a porphyry system, you get really low arsenic in epidote, and we've got an arsenic low in our epidote chemistry, and our titanium strontium gets high when you get close to the porphyry. So we're getting this coincident chlorite, titanium strontium high, and an arsenic low that basically nails the location of the Taldy Bulak deposit. Just quickly to wrap up, I'll give you one other quick example. Some of you have seen me talk about this a few times. We've just got a paper coming out on this one online in Economic Geology if you want to have a look. And it really shows you how few samples you can use to help you do this vectoring. We're looking at the resolution porphyry copper moly deposit in Arizona, 1.6 billion tonnes at 1.4 copper and 0.03 moly. So it's not the biggest porphyry on the planet. It's certainly a very big porphyry. There are bigger ones, but it's one of the highest grade. So it's a really sweet high-grade resource, and it's undercover. You're looking at the range front. We're in the town of Superior looking east, and everything on top is tertiary volcanics. Everything below that is Paleozoic carbonates and Proterozoic sediments, and the resolution porphyry is Cretaceous or Laramide in age, and it's lurking back there under the hill and you can't see it. So if we look at a 3D sort of overview, we were looking at this mountain range from the town of Superior. So this is the tertiary volcanic cover, and the resolution porphyry is buried under that tertiary volcanic cover in a little half graben that contains Cretaceous volcanoclastic rocks that do not crop out anywhere. You can see there's lots of smoke around the fire. These red things are epithermal veins that crop out in the Paleozoic and Proterozoic rocks. And for 100 years, there was mining of the magma vein, really high-grade vein and manto copper-silver deposit that varies from intermediate to high sulfidation in character. The discovery of resolution was from underground drilling from magma, when they first drilled into these Cretaceous rocks, and then eventually, with a lot of hard detective work, found this porphyry. So Rio Tinto sent us a suite of blind test samples from resolution. The resolution ore body you can see on this geologic map. This is the projection to surface. This is the tertiary volcanic cover on the eastern side of the map. And you can see the Paleozoic and Proterozoic sequence and all the epithermal veins cropping out through the range front. The town of Superior is sitting over here across a detachment fault. The samples that Rio Tinto sent to us, well, they're located here and here, 2 clusters of samples. And so when we were sent those samples, we didn't know they were from resolution. The samples were relocated into the Atlantic Ocean, so we couldn't use the sample coordinates. And you can see what we had was 2 clusters of 12 samples in total to do mineral chemistry on. 2 kilometre spacing, 500 metre slide offset. So you look at that, you go, well, have we got 2 prospects? Have we got 2 sides of 1 prospect? Is it something else? What does all this mean? If we project them onto a north-south cross-section, we can see we've got a cloud of samples that are from fairly deep on the south side, and we've got a series of samples from 1 drill hole on the north side. Those samples have epidote and chlorite alteration, which is pleasing to see. They have very few epidote veins, which is disappointing. Usually if you're close to a porphyry, you see a lot of epidote veins. The only epidote vein we had was this little discontinuous beast that we can see here. When we get these samples, we always analyse them. We go thoroughly through them to look at their mineralogy, their textures, their chemistry, to see what we can get out of the rocks before we do mineral chemistry. One of the things that's obvious in the whole rock geochemistry but wasn't obvious in the visual inspection of the rocks is they're very strongly potassically altered. We stain the rocks to highlight the orthoclase alteration. You can see very strong orthoclase alteration. You can also see there are little pyrite veins in some of the samples that have clay alteration halos. And so we're seeing pyrite present in these epidote and chlorite bearing rocks. 9 of the 12 samples contain pyrite, little pyrite cubes you can see there. And some of them contain pyrite veins. And you can see there's an increase in the sulfur content of their rocks as we go down the drill holes. As we looked petrographically, we could also see a little bit of chalcopyrite in some of the samples and quite a bit in others. And you can see quite high copper deep in this drill hole. So you'd get interested from the geochemistry, from the alteration, and you know, say that there's something going on at considerable depth in this deep drill hole. Okay, so what does it all mean? Are these samples all connected? If it is, with potassic alteration and pyrite, maybe it's a giant system. So maybe we're close to something. Certainly the signs are it is a porphyry system, but the epidote chlorite isn't really strong. So what do we get out of the mineral chemistry? Well, here's an epidote laser ablation map. This is a little grain of epidote, and you can see the arsenic is concentrated in the epidote rather than in the surrounding material. Epidote loves arsenic, it loves lead, it loves antimony. This has got pretty low antimony, this particular epidote grain. This is the rock that epidote grain is from. So we've got our trace elements in epidote that we usually see around a porphyry, but actually it turns out the signature here is subdued. That arsenic, antimony and lead is not as high as we've seen in other systems. So here's a little arsenic antimony data cloud, and it shows you a bunch of arsenic antimony analyses from epidotes from a bunch of porphyries. Metamorphic epidote tends to plot right down off the bottom. Often the antimony is below detection limit on the laser ablation, so metamorphic epidotes are easily screened out by having low pathfinder elements. The really big porphyry copper deposits, when you're far away from them, they have lots of arsenic and antimony, and so they plot up here at the top of this data cloud. The smaller porphyry deposits tend to have a more subdued arsenic antimony signature, and they can plot in this region here. But our problem is the arsenic and antimony contents change with distance from the deposit centre. So when you're close to the centre of the deposit, you get low arsenic and antimony, and when you're far away, you get higher arsenic and antimony. Sounds a bit counterintuitive, but it's what we're seeing in many of these systems. So the resolution data, which is shown in red, it could be distal to a small porphyry deposit, or it could be proximal to a high porphyry deposit. So the epidote by itself doesn't resolve that question. The reason why it might be proximal to a large deposit is because epidote is co-precipitating with pyrite. So these are a pyrite laser ablation map, and I just draw your attention to arsenic. Pyrite soaks up arsenic. So when epidote is co-precipitating with pyrite, the arsenic prefers to go into the sulfide mineral rather than the silicate. Arsenic is forced into epidote distal to porphyry systems when there's no sulfur for it to bond with. It gets forced into the epidote structure. Copper goes into chlorite, zinc goes into chlorite, antimony and lead go into epidote. So these silicate minerals take up the metals when you run out of sulfur. And sort of try to illustrate that with this cartoon here. These different geochemical domains around a porphyry, a potassic core where you're getting your chalcopyrite, you're dissolving calcium out of plagioclase and hornblende, you're dumping out biotite and magnetite and orthoclase. The calcium fluxes out and you run out of potassium and you start to produce calcium-bearing minerals like epidote and calcite, magnesium-bearing alteration minerals like chlorite. chalcopyrite, you run out of copper, you start to produce pyrite, so you get a geochemical domain where epidote, chlorite, pyrite coexist, and then you run out of hydrogen sulfide, and then metals which go into sulfides start to get forced into silicates. And so epidote and chlorite start to scavenge up a bunch of distal pathfinder elements. So that's why we think we see these different geochemical domains, and we've noted that the really big systems tend to have the most anomalous trace metals in the silicates peripheral to them, and we can pick that up 4 or 5 kilometres away. Sort of illustrated in these little cartoons. This is just a composite of arsenic, antimony and lead from epidote going with distance from deposit centres for a series of porphyry deposits, and you can see how the arsenic and the antimony are really kicking up with great distance and they're quite subdued close to the deposit. The resolution data set looks like this. So it's consistent with the proximal data. If we look at elements that decrease with distance away from porphyries, you can see again resolution. Well, it's not quite proximal, it's not quite distal, it sort of looks like it's this 1 to 2 kilometre distance from deposit centre. And if we look at the epidote lead chemistry, if we really want to go nuts and domain it, and it's a really small data set, so this is a bit silly to do, what we can notice is that the epidote from this southern cluster of samples has a proximal lead signature. The epidote from the shallow northern samples has a distal signature. The epidote from the deep northern samples has a proximal signature, suggesting that maybe there's a centre to the system in between and further away from the shallow northern samples. Not very convincing, but that's sort of what we could get out of the epidote chemistry. If we look at the chlorite chemistry, chlorite behaved really nicely. So we have chloride analyses. These are just the trace elements. Titanium tends to be high in chlorite from high temperature environments, and strontium, lithium and lead are high in chlorite from lower temperature environments. And you can see there's really consistent spatial patterns in those elements. If we ratio these to sort of amplify the signal to noise sort of response and look at proximal versus distal, we take our titanium strontium proximeter and we look at those samples in space. So here's our titanium strontium ratios for those samples averaged out, and we actually look at calculating the distance to the deposit centre using that Batu Hijau proximeter. For that blue dot, that's the prediction to the deposit centre. It's actually a 3-dimensional sphere, but we're looking at it in cross-section, so it's a 2-dimensional circle. If we look at all the predictions of distance to deposit centre, they're actually really coherent, and they coalesce at depth and give us a drill hole target based on 9 chlorite samples. Okay? And that target sits just below the resolution ore body. So we sort of overshot the mark, but you would have had to drill through the high-grade ore zone to get it. So actually, oh sorry, it was 10 samples, not 9. So that was a really great response. The reason it worked so well was because the cross-section passed right over the deposit, and chloride is sensitive to temperature, and the intrusive complex is the heat source. So if you were tangential to the deposit, you get a more subdued response that is much more difficult to evaluate, but still can be done. So that, I think we've hit the 4:30 mark, so I should really wrap up. Hopefully you can see that there is quite some interesting things going on in the research space in terms of looking at magmatic and hydrothermal minerals and their potential to discriminate mineralised environments and maybe provide indications of vectoring and fertility, so both fingerprinting and footprinting. The uptake of these techniques is not as strong as you might hope as yet, and I think it's really because no one can put a hand on their heart and say these have made a significant contribution to a porphyry discovery as yet. Fingers crossed that's going to happen sometime in the next decade. We have been applying them in different geologic environments, and that's what we're doing up in northwest Queensland at the moment with the sediment hosted in the ICG systems, and plenty of other people are pursuing this type of research all over the world anyway. So I think we're going to see more of this. At the moment, the measure of industry engagement is reflected in the fact that many of the commercial labs don't offer this type of ICP analysis as a service, although there are some that are now using uni labs to provide them with that service. We've just signed up with one to do that. So hopefully we'll see more widespread uptake of the technique, because we do think it does add value and gives explorers another tool. So with that, I'd just like to thank the supporters of our research program, to all of them. They've really been helping us work through the challenges of unravelling mineral chemistry and exploration. Thanks for listening, everyone.
Thank you so much, Dave. Now, we've already got some questions, so if I read them out for you. Patrice de Caratat is asking if any of the strontium isotopic trends accompanying the strontium depletion in these porphyry settings. Are there any strontium isotopic trends accompanying strontium depletion in these porphyry settings?
Okay, so that's a great question, and my answer is I don't have the data to be able to say yay or nay. I have very limited strontium isotopic data that we've generated over time, and generally we're not seeing big isotopic gradients in the strontium. We're seeing a predominance of magmatic strontium. It's really challenging when your intrusions are mantle derived and the volcanic host rocks are mantle derived, you don't get a strontium gradient. So at a place like Resolution, where you've actually got continental crust and you've got really strong crustal versus mantle gradients between the wall rocks and the fluid source, strontium has great potential to provide an additional vector. Just haven't done the work at Resolution. And many of the porphyry systems we've worked on are actually hosted in arc volcanics, so we just don't see much strontium gradient. All
right. We also have a comment rather than a question from Ian saying, fantastic, David. So that's good.
Thank you.
Does anybody else have any questions that you'd like to ask while we've got Dave or Joe or Phil or Dom on the line?
Dave, I've got a question while other people are thinking up theirs.
Sure,
how would you recommend, I think there's quite a few explorers online. How would you recommend that they apply this technique to their exploration programs?
Yeah, so that's one of the things we've been trying to really get sorted, Rick, is where does this fit in your exploration workflow? Often what we see, because we do get commercial jobs coming to our laboratories, and people often are sending us samples really late in the exploration cycle. So they're trying to use it as a Hail Mary. Like we've done everything else and nothing's working. Oh, well, we may as well try a bit of Epidote or Chlorite and maybe it'll work. And usually it doesn't, and there's a reason for that. And it's the same reason nothing else was working, and that's because there's nothing there. So we would hope that it actually gets adopted early, right? So when you've got really sparse data. So we are thinking about that question, that as we go exploring undercover, maximising knowledge out of your drill holes is key, right? So every drill hole is a huge investment if you're drilling undercover. And if you drill through it and all you hit is a bit of green rocks, this is something you can do. You can look at the trace element chemistry in those weak alteration minerals to see if there are signs of life. So I would hope it's being used at that point. If going into a district where there is a little bit of outcrop, it can be used to try to help you sort of work out, have we got the right flavour in those rocks? There is potential for trying to use dating of some of these hydrothermal minerals as well. That's some of the research we've been doing recently to try to sort out, say, metamorphic versus hydrothermal questions as well. So there are various approaches you can use where this thing can augment what you're doing. And really getting, for the porphyry systems, it looks like that sort of a 300 to 500 metre sampling grid across an area that's 10K is sort of what you want. So if you had an outcrop like that, that's what you do. For a sediment-hosted base metal system, Rick, I'm really scratching my head. If the whole basin is part of the system, if the damn thing exhales, you're dealing with a completely different scale of problem. So I think each system's going to have this scale dependency we've got to work through on how to sample the background. And yeah, depends on the nature of the system as to how broad your samples are going to be and what you would actually sample to get the signature that tells you you've got signs of life.
Great, thanks.
All right, David Biggs is asking of Phil Main, I believe, do the background ML predictions use wavelets?
Sorry, I'd have to actually dig into what we run. But just as a brief overview, what we're using is a random forest approach on log transformed data. I'd have to actually dig into them to see if we're using a wavelet transform.
And then back to Dave again. Jacques Batumike is asking, hi Dave, this moves out of the general idea of drilling moly, bismuth, etc. anomalies. Do you think that we should use this as a layer of information to the usual exploration workflow before drilling? This is because a lot of moly anomalies drilled do not deliver.
I think that it would be helpful to gather this information before drilling if you can. If you can actually get the actual fresh rock or the altered rock to do this, you will potentially get some additional signs as to whether you're in the right environment or
not. Okay, so we don't have any more questions. If anybody else has anything they'd like to ask our panel, please feel free. Otherwise, we might start feeding everybody into the drink session, which means that Rick and Matt have to make everybody panelists so that you can all see each other. We haven't found an easy way of doing this yet, I don't think. So if you don't want to stick around, then hang up. But if you do, we can have a bit more discussion around some of the talks that we've heard, and to catch up with how everybody's going in our digital world. And don't forget as well that you will hear some more of this style of work from Sean Barker from Codes in 2 weeks' time at the webinar, which will be a presentation of the Geological Survey of Queensland's collaborators on a number of projects focused on prospectivity in the Northwest Minerals Province. So Sean will talk about some of that work, and next week Rick Valenta has assembled a fun and motley crew of presenters to talk about their favourite rocks from the Northwest Minerals Province, and as he said, it will be an unconventional presentation of deposits and samples from that area. So it should be a lot of fun.
It's funny when you start asking people to talk about their favorite rocks, what I found is that they can't resist sending you pictures of their favorite rocks ahead of time.
We're all the same.
And there are some very nice rocks in there. So I think it'll be a treat. Perhaps easier on the mind than today, but there's some very nice rocks there.
Now, Ian Wolf has just asked another question. He would like to know how many people attended. So we had over 100 people in the webinar. And so great job, everybody. And thank you to everyone for coming. All right.
Okay. Lots of people have stayed around.
I know. It's great. We won't have room for them all.
Now everyone's been elevated to a participant. You can turn your webcam on, you can turn your microphones on, and you can talk. So please do. Please join us.
Please join us all.
Mike, click in.
I'm sure Mike has some questions or comments.
Well, which Mike? Yes.
Mike Whitbread, actually, but...
Oh, that MMI stuff, it comes up everywhere, doesn't it?
I was waiting for your comment on that.
I kept it fairly PG, I thought, during the question and answer.
Well, I'm going to say hello to Tom Klein, who's joining us from down in New South Wales.
G'day.
From
Hi, Tom.
Silver Mines. How are you going?
Yeah, good. It's nice and raining here, so it's a good day to be indoors.
Fair enough.
John Anderson, how are you?
I'm great, thanks, Rick. Great show, everybody. Well done.
Nick,
Thanks.
long time no see. Nick can't hear me.
Nick's not listening.
No. He's stuck.
Nick's working on his Bluetooth.
Yeah. G'day, Ian.
We've got several pages of people now, so you can all see
Yeah.
each other. The only problem with this forum is that only one person can talk at a time, so it kind of stifles free-flowing conversation. But
You can set up, actually, no, you can't. On a webinar, you can't actually set up, like on a normal Zoom meeting, you can set up breakout rooms. So if two people, decide that they want to go off and gossip about someone in a corner, they can do it in a normal Zoom meeting, but they can't do it in one of these webinars. You're forced to address the entire group.
yes. So who was that?
I was just going to say hi, Oscar, and Lauren, another faithful regular attendee. So thanks
Yes,
for coming.
she's been great. And who else do we need to say hello to? Sean's there. He's hiding himself. Sean Barker.
Yep, I'm hiding. I'm manipulating I'm actually manipulating mineral chemistry databases for Dave at the moment. So.
Right.
Work harder.
Yeah.
Where's your dog, Sean?
Where's my dog? Sleeping. He was annoying me earlier when you were talking.
Oh, good.
Your dog seemed to settle down, Dominic. That was good. He didn't trouble us during the talk, I don't think.
I just muted myself as the dog's barking.
Oh, right.
Oh, Ziggy's joined us from WA as well.
Yep, the main outcome of me giving lectures was after 3 lectures, the students just asked to see my dog at the end of the lectures rather than any of the lecture content. So
Yeah.
I'm not sure if that said something about my lecturing or something about the effect of dogs, but anyway.
Yeah. I guess everybody's sort of collecting a list of dogs, people's dogs that they've met and getting to know the people's home workplaces and which ones are messy and which ones are neat. And, oh, there's Tom's dog. He's going, what the hell are you doing?
So in case everybody didn't see, Dom put all the links to various geochem data sets in the chat feed. So you can get hold of any of those. And I don't know, I'd love to know who all these other people are. Do you know, is anyone you want to point out, Rick, and draw them into the conversation?
I'm just trying to see David Carrasco's name. I know. I feel like I know you, but I just can't place the place where I know you from. Or maybe it's just I know your name. Or maybe this is one of those.
While we work that out, Nick Diru's here, and he gave an amazing talk for his final PhD presentation today. So I was fortunate enough to be able to catch that. So I think that's pretty big. And poor guy couldn't even go and celebrate afterwards.
Yeah,
I did a little bit.
Just a little bit. Yeah,
I had a couple.
Yeah.
Well, I hope everybody's got a drink. I actually didn't get one, so I'm going to run off now and come back with a drink.
Yeah. So, how long can you celebrate for, Nick, before you got to put the nose back to the grindstone for the final push to the finish?
At least another 24 hours, I think.
All right. Fair enough, too, I think. Yeah.
Fair enough too, mate.
Take the weekend, start in on Monday.
All right. No
or
worries.
Tuesday. Monday's a holiday.
That's official advice. Perfect. That's good.
Yeah. Yeah, that's right. Yeah. Ziggy, how are you guys going? Are you managing to get some field work done? Somebody's going to write a book on human interaction in Zoom things. People who are
this isn't that different from some science departments though, because it's really hard to get people talking when they're face to face sometimes as well. So I think you're doing a commendable job, Rick.
Yeah, it is hard. Well, we had a session last week where, you know, that was just a normal meeting, and we divided. We had like 60 people, and we divided the people up into 9 different breakout rooms. And I was a host, so I went to all the different breakout rooms. And in all the breakout rooms, everybody was chatting away and acting and you know, talking about things. And then they brought them all back together again and said, "So, what does everybody think about this?" And it was just no response at all. I think it's just people look and they see the massive faces and just can't can't bring themselves to talk, except for, you know, those of us who have no shame, but or like John Anderson, for example, who can talk underwater in front of any group. So how's life, John? How are things in Adelaide?
Well, best to say quiet, Rick. Thanks very much. I guess all I can say is I can see Ian Garsted there, so the XMIM South Australian crew is well represented.
Yeah. What are you up to these days, Ian?
I'm trying to learn how to unmute my computer first.
Right.
Well, pretty quiet here, Rick, in the Adelaide Hills. I'm envying all these people I can see that look like they're in warm climates.
Yeah, it's warm in Brisbane still.
Yeah. Now, it was a little cold. It only got to 29, I think. So it's, you know.
Yeah, winter arrives next week. I think we get 24s or something.
Oh, so excited.
Yes, well, I got down to 4 this afternoon here. So.
Yeah.
But pretty quiet here, Rick. Well, I'm isolating and being socially responsible. And,
right, yeah. Yeah.
Doing lots of reading and very much appreciating these series of seminars, webinars you've been doing.
Oh, that's good. Yeah. Well, it's you know, I think it's something that we probably, well, I don't, you know, I guess we have to talk about what we do with this one, but I know with some of the ones that we do, you know, we have one every Friday morning, and that's just going to be now a webinar forever, because you get, you know, it'll be the best of both worlds. Then, you know, people will come in and they'll be able to sit in the room and have their you know, and then have their cup of coffee and bicky afterwards. But the people who are, you know, other people who are interested can just dial in. So all I've got to do is work out how to get both going without turning it into a technological nightmare. But you know,
you could have a second link for the after drink session, so then you can get into the rooms.
Yeah, that's true. Actually, you could just send a. We could do that actually, because we could just send a Zoom invitation to, because when people sign up, of course they get a they get a, you know, there's an email address that can be then emailed to send a separate Zoom link that would then, but they would then have to go to the host and say, "Oh, I want to go off and talk to so and so in a separate room." It makes me feel a bit uncomfortable, but
oh, you can't just move yourself between the different
no.
Oh, right.
That's something, you know, these are all in. If we should be, well, we are recording this. Actually, I should be. I get scared to turn the recording off, because I'm going to try it now, because every one of these webinars we run,